Welcome back. Today let's continue examining the zeros of polynomial functions. We'll consider other techniques. The first technique is Descartes' rule of signs. In 1637, René Descartes realized that if you count the number of sign variations for consecutive coefficients, it would give you the maximum number of positive real zeros. Before we can use this theorem, we need to make sure that the polynomial is written in order of descending degree. And we're going to count the number of times the sign changes from positive to negative. Now, that's the maximum number. Well, the total real zeros, positive real zeros, can actually be less than that number by an even integer. If we plug in and substitute negative x, the number of variations of f of negative x would be the maximum number of negative real zeros for that function. But there can also be less by an even integer as well. Even though this theorem is in Descartes' name, there are many mathematicians that looked into it, including Isaac Newton in 1707 and Gauss in 1828. In 1828, Gauss was the one that realized that this not only gave the maximum number, but it had to decrease, if at all, by 2. Because if you remember, complex zeros, imaginary roots, occur in conjugate pairs. So if we have a plus bi as a root, then its conjugate, a minus bi, must also be a root. Okay, let's consider the number of changes. So here we have f of x, and we're literally just going to count how many times the sign changes. Before we look at the number of variations, let's first look at the total, right? This is a cubic, so this will have a maximum of 3 roots. So I'll put 3 over here. That's going to be the max. Now let's count using Descartes' rule of signs. So we go from -2 to 5. That's one change. +5 to -1. That's another change. -1 to +8. That's another change. There's 3 changes total, so there's a maximum of 3 positive roots. Well, since we only have a total of 3, there can't be any more negative or imaginary. Okay, let's consider the negatives. When I substitute with negative x, I'm going to plug in negative x wherever I see x, and you can probably see it pretty quickly that signs are going to change. So f of negative x will equal positive 2x cubed, positive 5x squared, positive x, and plus 8. Those numbers are all positive, so there are no negative roots and no variations. So we can confidently say that there are no negative roots, real roots at least. Okay? Well, we know that imaginary numbers, complex conjugates, occur in pairs. So it is possible that we have 2 imaginary roots and 1 positive. Remember, those have to occur in pairs, so the positive real roots decrease by an even number. Now let's consider a second technique, which considers upper and lower bound rules. It's also called the boundedness theorem. We're going to use synthetic division to determine an upper bound or a lower bound. If you have a number c that you're using as your k in synthetic division, and your last row of that synthetic division is either all positive or 0, then that number is the upper bound for the real zeros of f, meaning that there are no numbers greater than that value that are going to be zeros for that function. If you use a number that's less than 0 and the number is or creates a last row that alternates between positive and negative, that value is the lower bound, meaning that there will be no values less than that value that are real zeros for f. So let's look at this one. Here we have the function. It's written in descending order of degree, and we're going to check for the value 4 and see, is 4 an upper bound? The coefficients are 1, -1, 3, -8, and -8. I bring down the 1. Remember, we're multiplying, going up, adding, going down. So we have 15, 60, 52, and that'll be 208 or 200. That's the remainder. When we look at that last row, they're all positive numbers. So we can say that x equals 4 is an upper bound. For the function. There will be no numbers greater than 4 that will be zeros for this function. Now let's look at a lower bound. And we're going to see, is -1 a lower bound for this function? So -1 will be my k. The coefficients are 1, -1, 3, -8, and -8. I'm going to bring down the 1, -1, which is -2, 2, so that's 5, -5, that'll be -13, and 13, 5. If we look at this, each time it changes from positive to negative, +1 to -2, to +5 to -13, to +5. So these are alternating. That confirms that x equals -1 is a lower bound for the function. Now let's put it together. Okay, so we're going to use both of those theorems, Descartes' rule of signs, the boundness theorem, and also the rational root theorem, to solve and find all the zeros for this polynomial without a calculator. Okay, so the first one, we want to make sure we see how many positives, how many negatives, and how many imaginary roots there could be. So I'm going to use Descartes' rule of signs. And let me make a little table. So we'll have positive, negative, imaginary, and total. So when I look at the number of variations in the sign, well, we have 1 right here, and then this is negative to negative, and then -11 to 14. So that's 2 positive real roots. Remember, this is a cubic, so we're going to have 3. Now let me plug in f of -x to confirm how many negative roots we'll have. So I'm going to plug in -x cubed minus 7 -x squared minus 11 -x plus 14. We'll have -x cubed minus 7x squared plus 11x plus 14. You can see right here, from that -7 to the +11, there's 1 negative root. So if we have one negative root, two positives, we would have 0 imaginaries for that possibility. Now we know that the positive number of roots can decrease by an even number because the imaginaries occur as pairs. So another combination would be 0 positive real roots, 1 negative. Okay, that one can't go down, so there has to be 1 negative, and 3 total. Now I'm going to hone on to the 1 negative. Okay, so there has to be 1 negative. There could be 2 positives, there could be no positives, but we know for sure there's going to be negatives. So let's generate the number or the possible roots. So we're going to use the rational zeros, right? We're going to look at those P over Q's. So when we look at the P over Q's, we're looking at all the factors of the constant and all the factors, sorry, it's hard to write on here, and all the factors of the leading coefficient. So we're using the rational zero test here. So when I look at the factors of P, well, the factors of P are going to be plus or minus all the factors of 14. But my Q is just 1. So it'll just be plus or minus 1. So all my possible roots would be plus or minus 14 and any factors of 14. So plus or minus 7, plus or minus 2, plus or minus 1. So we have 8 possibilities here, and one of them has to work as a negative real root. Okay, so for a negative real root, I'm going to use, well, for this one of them has to. Okay, I'm going to try them out. So I'll try one kind of in the middle for the negative. So I'll try negative 7. So when I try negative 7, I'm going to choose a different color here. Okay, so when I try negative 7, my polynomial was 1x cubed, negative 7x squared, negative 11x plus 14. So let me try the synthetic division. So we have 1, negative 7, negative 14. 14 times 7 is 98. That'll be 87. 87 times negative 7 is negative 609. And that'll be, I'll put the remainder, negative 595. When we look at the sign changes, they alternate. We definitely know that negative 7 is not going to be a 0, right? Because there's a remainder. But we can see that the signs alternate. And knowing that the signs alternate, we know that negative 7 is a lower bound. This helps us to identify that negative 14 will definitely not be a 0. So I can put x equals negative 14 is definitely not a 0 because negative 14 is less than negative 7. So this is the boundedness theorem we're using. Okay, well, since we know that negative 7 is the lower bound, let's try the next negative. I'm going to try negative 2. So we know that negative 2, the coefficients are 1, negative 7, negative 11, 14. Synthetic division, bring down the 1, multiply going up, add going down, so we negative 9, 18, 7, negative 14. The remainder is 0. Okay, so we know that f of negative 2 would equal 0, so x plus 2 would be a factor. Remember, this is the factor theorem right here. So this was originally a cubic, and then we have a quadratic. So I have the quadratic x squared minus 9x plus 7. Well, we can plug that into the quadratic formula. So x equals, that'll be 9 plus or minus the square root of 81 minus 28 over 2. So the zeros would be 9 plus or minus root 53 over 2. So we have those two irrational roots, and then we also have the negative 2. So this will be x equals negative 2, and then 9 plus or minus root 53 over 2. So when we look at that chart again, we know we definitely have the negative root. And so it must have been 2 positives and 1 imaginary. Because even though they're irrational, they're still going to be real roots. For this last example, we're going to use polynomial models. Now we want to create pyramid-shaped trophies with a square base. And we want to use 24 cubic inches of resin to pour into the mold to create these trophies. Now the dimensions of the trophies, we want the base to be a square. So those would have side lengths of x and x. And we want the height to be 5 inches more than the length of one of those sides. So we can represent the height as x plus 5. Now to write the equation for volume, that's 1/3 times the area of the base times the height. So the area of the base is x squared. The height can be represented with x plus 5. So the volume would be 1/3 x squared times x plus 5. Now if we're given 24 cubic inches of resin, we can substitute volume with 24 and solve for x. So let me multiply everything by 3 to get rid of the fraction. So we get 72 equals x squared times x plus 5. Let me distribute x squared. So that's x cubed plus 5x squared. And then set this equal to 0. Now all the possible rational roots can be represented with p over q. And our p is 72 and our q is 1. So all the factors of 72 are 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. Now remember, our x, what we're solving for, has to be one of those side lengths. So we definitely know it's not going to be a 72, right? Because the total volume, we'd have to square that, and 72 squared is already big. If we divide it, we can't get close to 24. So it has to be a smaller number. So I'm going to pick a smaller number, maybe 6. Okay, again, the coefficients were 1, 5, 0 because there's no x, and negative 72. So when I plug that in to synthetic division, I get 1, 6, 11, 66, and then 66 times 6, 396, remainder of 324. Well, we know that that's definitely not going to be a solution, but we also know because everything is positive in the last row that x equals 6 is an upper bound. So we don't have to try any numbers greater than 6. Let's try the next one. Let's try 4. So again, the coefficients are 1, 5, 0, negative 72. So that's 1, 4, 9, 36. 36 times 4 is 144. And that would have a remainder of 72. Again, it's not a solution, but we can see that x equals 4 is an upper bound. And we already knew that because we already tried 6, but so 4 wasn't a solution, then we knew that nothing above 4 would work. All right, let's try the next one. Let's try 3. So coefficients again, 1, 5, 0, negative 72. Bring down the 1, that's an arrow. 1, 3, 8, 24, 24, and 72. So we have our answer. So our solution is x equals 3. But this is a word problem, so we want to make sure that we give our answer in words. So the base of the trophy has dimensions of 3 inches by 3 inches, is a square, right? And the height of this trophy will be 3 plus 5, or 8 inches. Thanks for spending time with me today. I hope this lesson was helpful.